All right. So the graph of rational function is kind of continuing where we started. Holes. If an x value is a 0 of both the numerator and denominator, then x comma f of x is a hole. So we saw that yesterday when we ended up canceling out top and bottom the same factor, then whatever made that factor equal to 0 would be considered a hole. And what happens with holes is your graphing calculator will not show them. It's not specific enough. It won't show up. So you have to find the hole by hand. And the way you do that is by plugging the x value of the hole into the reduced function to find the y coordinate. If you plug it into the original, it will give you an undefined 0 over 0. You got to plug it into the reduced function. I'll show you what I mean by that. So just like yesterday, we're going to start by factoring. Okay. So what are the factors at the top here? Yeah, it's negative, so 2x and x, minus 1, minus 2. And on the bottom is the difference of squares. So it says on here, find all asymptotes and any holes in the function. So the x minus 2 factor gets canceled out. So my vertical asymptote is going to be x equals whatever would make the bottom 0 that cannot be canceled out. So x equals negative 2. I usually look at the original problem to identify the horizontal asymptote. It's written in standard form with the leading coefficients being the highest powered terms. 2x squared over x squared reduced to what? Just 2. So y equals 2 is the horizontal asymptote. And then the hole, I know the x coordinate of the hole, it's whatever would make this 0, which is x equals 2, right? So the x coordinate of the hole is 2. The y coordinate of the hole we find by plugging in 2 to the reduced form of this. So f of 2 equals 2 times 2 minus 1 over 2 plus 2. 2 times 2 is 4 minus 1 is 3 fourths. So at 2 comma 3 fourths we have a hole. So we can find out like that. And that will not show up on your calculator. If you run a table, you'll see it too. It'll be undefined. If you want the exact coordinate, y coordinate, where that hole is located, you have to plug it in to the simplified version of the rational function. Okay. All right, the next one is we have a cubic on top, so we're going to have to use our techniques that we learned with the super zero stuff, right? Probably not complicated zeros since I'm asking you to cancel and find holes. So, what are the possibilities here for zeros? It's minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So please find a 0. Which one of those is a 0? We split it up. Try one. Try negative 1. Try 2. Let me know when you found the first one. is when work. Justin said one word. Should we go for it then? So if one worked, that's always convenient. So okay, one worked. So this thing is going to factor as x. If 1 is a 0, it's one of the factors. X minus 1. And I'm left with x squared minus x minus 6 equals 0. How does that factor? I don't really need the equals 0, I just need the factors. Where factors of negative 6 that add to equal negative 1. Yeah, x minus 3x plus 2, okay. So x minus 3, x plus 2. And on the bottom we have, what kind of factors? Looks like an x plus 2 and an x plus 1, right? So, that's all we need. Factors top and bottom. X plus 2's cancel out. That's my vertical asymptote. Is x equals negative 1, because that would make the bottom 0. Cannot be canceled out. What about horizontal asymptote? Looking at my leading coefficients. Oh, there's not, right? Because the power on the top is bigger than the power on the bottom. Now, no horizontal. Could I have an oblique? Yes. Let's find the oblique. Well, the oblique occurs when the top is just one more than the bottom. So we've already done some division here. Do you see that? Canceling is division. So I can take negative 1 and divide it into whatever I get when I multiply these two out. Okay. So negative 1 into, what is this thing I'll multiply out? Let's see. This is x squared minus 4x plus 3. So it's 1, negative 4, 3. And down the 1. And so my oblique asymptote is what? It's y equals, it's right here. It's x minus 5. This should not be a 0. It should be an 8. It should be an 8, but we ignore the remainder. Doesn't matter if the remainder is 0 or something else. What's left here is our oblique. So it's y equals x minus 5. And then the whole. What's the x coordinate of the whole? Negative 2, yeah. And then the y coordinate, we can take what's left over up here in factored form. Plug in negative 2. So we have negative 2 minus 1, negative 2 minus 3. Let me demo that here. So you're okay with the oblique? Which one? Doing the long division. So we have r of x equals so r of negative 2 equals negative 2 minus 1 Negative 3 times negative 5 is 15. 15 over negative 1 is, I'm getting negative 15. Yep. So negative 2, negative 15 is the whole. Clean this up a bit. So the oblique asymptote no horizontal asymptote, and the whole at negative 2, negative 15. Yeah. Well, this is positive on top. Negative times a negative, and then this will be negative on the bottom, so it will be a negative 15. Right, yours didn't turn out very well, but on there you should see what would make up like an aluminum can or soup can. You have a lateral area, which is a rectangle, and 2 circles that make up the top and bottom. So we're going to do a mathematical modeling problem and set up something that it looks rational here, a rational function. So that's how it connects to this section. So it says the Reynolds Metal Company manufactures aluminum cans with a capacity of 500 cubic centimeters. The top and bottom are made of an aluminum alloy that costs 0.05 cents per square centimeter. So yes, that's 5/100ths of a penny, so not very much cost. The sides are made of material that only costs 0.02 cents per centimeter squared. To express the cost C of material as a function of the radius R. So this is made up of 2 of these guys. This is a pi r squared here. So maybe off to the side, on yours it's all grayed out. Write pi r squared and pi r squared. So we're going to write an equation to represent the cost of this, which is based on the price times the surface area. So the pi r squared, the yellow parts there, happen to cost 0.05 cents per centimeter squared. So we have C of R, cost equation, equals 0.05 times the sum of the 2 circular areas here, which is 2 pi r squared. Then it says the sides are made of material that only costs 0.02 cents per centimeter. So that's going to be 0.02 times the cost of the lateral area. Now, if you take a piece of paper and you fold that, you basically have a cylinder, right? There's my cylinder right there. If I open up this cylinder, I have a rectangle. The length of the rectangle is the same as the circumference of the circle. So we call this the height, this vertical portion the height, and this horizontal portion we call the length, and the horizontal portion is 2 pi r. And then we have height. So it goes like this. There's h, and this portion from here to here is 2 pi r, which gives us a lateral area. The blue lateral area is 2 pi r h. So we're going to call this 2 pi r h. So that's part of express the cost, CL, the beginning part of the material as a function of the radius r. So what we're saying here is we want a function with only one variable, and that variable needs to be r. Right now I have 2 variables in it. Once again, pi is not a variable, it's a constant. But I have r and h in here. So there was a little bit more information given. It said the volume of this can, right here, this is volume equals pi r squared times h. I want to write that down. That's the volume of a cylinder. It's the circular base times the height. And it was given that that is equal to 500 cubic centimeters. And so the key to writing this problem as a rational function in terms of just r is to use substitution. So with that volume formula, combined with the surface area formula, I can go ahead and plug this equation right here. I can actually solve it for h and plug it into the formula up here. So I would divide each side by pi r squared. So I have h equals 500 over pi r squared. So I start with the volume formula cylinder, plug in what's given to me, the 500, solve for h, and then I'm going to take this equation and plug it in for h up here. It'll be a little messy, but I'll have an equation just in terms of r. It's 2 pi r, and then in place of h, I'm going to put 500 over pi r squared. And so the pi's cancel. One of the r's cancel, leaving just one r. And I'm left with T of r equals 0.05 2 pi r squared plus 0.02. 2 times 500 is 1,000. Over r. Then one more step. 0.05 times 2 gives me 0.1 pi r squared, and 0.02 times 1,000 gives me 20 over r. So I have a rational function because of this 20 over r term. So that's part A. That's my equation. You gotta multiply the cost times each of the pieces of the surface area of the can. I have to study that example. I have one like that on the code sheet. It says graph the function. So when we say graph the function, we mean on your calculator graph it. So go ahead and graph this on your calculator. Instead of r, you'll have x. And then I want you to find what value of r will result in the least cost. Which function is that in the calculator? So go ahead and do that. So after you graph it, I usually start with standard graphing windows. It looks like I need to see this branch up here. Actually, my minimum is going to be right about where my arrow is, okay, in that first quadrant. I'm not going to care about this blue piece coming through here. I care about the one in the first quadrant. It's a real life problem. I'm looking for positive value. So, you know, if I were to change my window, I might say, okay, let's make it a y max of, say, 20, and go up by 2s, and then graph it later. That piece zips on through. There's the other piece. I could estimate, it looks like a radius of around 3 will give me the minimum cost. Okay, that's what I'm trying to do, is minimize my cost for making those aluminum cans. So I go to second, calculate the minimum 3, and the left bound there it is. So there's my left bound, maybe somewhere around 1.2. Right bound, maybe somewhere around 4. And give it a guess. And the output it's giving us, the x value is the minimum, or is the radius that minimizes the cost. And the y value is not really the y value, it's the cost per can in cents. Okay? So what this is telling me is, if I have a radius of 3 point, what are the units in here? 3.1 169 centimeters, my cost will be about 9.5 cents per can. That's the minimum cost. So, adjusting the radius of that can makes a difference in how much my cost will be, and then when you're making millions and millions of these, it makes a difference. So, part B on here. Ask the question, graph the function. Okay, we did that. So B is the graph. All we really care about is this little piece up here. C says what value of R will result in the least cost if R equals about 3.17 centimeters. D, what was the cost per can? 9.47 cents per can. So once you have the function, you can then use the calculator to get your value X, or in this case R, to give you the minimum cost.